Hello and welcome everyone to the next event in our webinar series, a presentation by Thorlabs Solutions Engineer Lucas Lamb. My name is Eric Kirchek and I will be moderating today's talk. Lucas received his Bachelor of Science in Applied Physics and Mathematics at NJIT and has been with Thorlabs since 2017. Originally an application engineer in Thorlabs' Technical Support Division, Lucas now supports customers by marrying Thorlabs' manufacturing capabilities with customers' unique and varied application requirements as a photonic solutions engineer. Throughout Lucas's talk, please feel free to submit any questions you have using the Q&A tool. He will be answering any questions at the end. Now I'd like to hand this off to Lucas.
Great, thanks Eric, and thank you all for joining today. As you can see on screen, we'll be discussing how to achieve long-term optical alignment stability within your system. So let's jump right in. So any optical system, just for ease of discussion, can be considered to be made up of three things. Your light source, some optics or medium or a device under test in the middle, and a detector or receiver at the end. This could be as simple as, say, pointing a TV remote aimed at your TV to turn on or change the signals, turn the volume up, whatever it may be. Or in the example pictured here, it's a very simple experiment with a laser light source passing through a neutral density filter to reduce the beam power and then splitting evenly through the beam splitter to hit both detectors A and B. In the TV remote example, eventually your arm won't be pointing at the TV to the point of misalignment and not being able to change the channel. Maybe your dog or pet might come and tackle you while on the couch and interrupt that optical connection. In this case, realignment is pretty trivial. You can point your remote back at the TV, but for the example pictured here and other setups involving lasers, optics, photodiodes, etc., the stability of your optical alignment will be more critical. So when it comes to optical alignment, all tunable components of an optical system and how they're fixed, held, or manipulated are going to be your biggest factors when it comes to alignment stability. In other words, optomechanics are going to be critical for maintaining that alignment. In the TV remote example, you can consider your arm or the hand the tunable portion, while in the previously pictured example with the filter and beam splitter, assuming your light source and detectors are fixed, which is also not often the case, the way the ND filter and beam splitter are mounted could be considered the tunable portions. Again, optomechanics in both cases are going to be the important factors. In most optical systems, mirrors are one of the most common optics used to steer a light source or laser, and kinematic mirror mounts are one of the most common pieces of optomechanical hardware to tip and tilt that mirror and redirect the reflected light along your beam path. While the principles of optical stability apply to any tunable component in your system, like light sources and receivers too, for simplicity, we're going to focus on the kinematic mirror mounts mostly for today's talk. So what are the common problem areas or sources of failure when it comes to optical alignment? Some of the biggest ones we've narrowed down for optomechanics include thermal instability, crosstalk, backlash and drift, and external vibrations. And why is this important? So a few key things that you want to think of are avoiding downtime from realignment. The research lab user, for instance, might have to realign their system each morning or maybe every half day, and that takes precious time. You can also avoid faulty systems from misalignment due to shipping and handling. So shipments of, say, black box laser systems by land, air, sea, they can be misaligned during shipment pretty easily, which voids the usefulness of the end product. And that leads to returns and extra costs for repair. So ultimately, it's pretty important to prevent those repair costs. And as a last note, you can avoid incorrect data from misalignment. If you get incorrect data, if the light is not incident on your photodiode or detector just right, it could lead to misinterpretation of results, which again takes more time to troubleshoot. Now, understanding why that stability is important, let's dive into those problem areas a little bit further. So these common problem areas can be found at nearly every tunable optomechanical component of your system. So it does feel like sometimes the universe is trying to misalign your system. When it comes to thermal instability, the lab or environmental temperatures can often vary from sources like the air conditioning, the number of people in the room, your equipment, since powered equipment needs to dissipate heat, and shipping environments especially. Component materials within your optomechanics can have different CTEs, or coefficients of thermal expansion, and thus change at different rates when the temperature changes. Machined materials can also retain internal stresses from the machining process, which lead to a temperature-dependent hysteresis, which is another way of saying it changes one way as you increase the temperature and changes a different way as you decrease that temperature. When it comes to crosstalk in your optomechanics, this can be defined as adjusting one axis and getting unwanted movement in another axis if not properly constrained. Wear and tear between those contact materials can reduce those movement constraints and over time increase your crosstalk, which affects your alignment stability. Think of the contact points of most mirror mounts where the adjuster screw pushes on the optic plate. Softer materials like some alloy steels or aluminum will deform faster than other harder materials, and those deformations create grooves or ridges or other items that could bias the motion by not properly constraining the movement across each axis. For backlash and drift, you can consider these any clearances or gaps in the parts that can lead to a slop in the motion. In the picture on the bottom right here, you'll see that the nut in a light gray on top is not perfectly made to the dimensions of the lead screw. So there's a little red line where the backlash is shown, and that little red line creates a gap or a clearance in the part where your lead screw and nut can shift back and forth with each other. Even a small amount can lead to a bigger optical misalignment down the road. Additionally, lubricant, often used on lead screws and any adjustment mechanisms, can build up in places and affect the motion as it builds up in one, slowly returns to kind of an equilibrium, and that return to the equilibrium form is where you'll get that movement. You can consider drift sort of a slow form of backlash. And lastly, external vibrations are a common problem area for alignment. This can be most likely shipping and handling is one of the more common sources of this. You can also break external vibrations down into seismic or anything coming through the environment, through your table legs or through the bottom of your workspace. Acoustic, any sound or air pressure differentials that will vibrate the surrounding air, or direct vibrations applied to your workspace, often a table or a breadboard surface. These can often be compensated by anti-vibration isolators or floating optical tables, but not all systems are going to have the luxury or space for a table, for instance. So now that we understand the problem areas a bit more, how can we measure if that optical system is stably aligned, or better understand how unstable a system is? Let's use the external vibrations as a quick example, and on the next slide, you'll see a potential worst-case scenario of external vibrations that could replicate earthquake effects on your optical setup. So as the video plays, for vibration testing, we put two mirror mounts mounted on 1-inch posts and secured them to a breadboard with clamping arms. Collimated lasers were then reflected from those mirrors onto two lateral position sensing detectors on the same breadboard to detect changes in the beam's pointing stability over time. The entire platform was then vibrated with a variable frequency and amplitude, and the displacement of the beam on the detector was recorded. Each grid line on that computer screen is going to represent a beam deviation of about 10 microradians. So as the test progresses, or as the video progresses, I'd suggest following along with the two plots red dots and seeing how they move between grid lines. So as you're starting to hopefully see, when subjected to vibrational frequencies as high as just about 100 hertz and accelerations as high as 6 Gs, the mounts here remain mechanically sound. The angular position of the mounts remains stable to within 10 microradians for both parallel and perpendicular vibrations. Now, let's take that same breadboard setup from the vibration testing and instead place it inside a thermal chamber where we can control the temperature. Rather than a multiple-hour video showing the change in temperature, let's depict the results graphically instead. Each plot shows a thermal shock or a temperature increase applied to the setup, with temperature shown by the orange lines and values noted on the right-hand y-axis. Over the course of about 1 hour, which you'll see just after the 50-minute mark here. So this first hour circled on the Mount 1. So as that temperature is increased by about 7.5 degrees, then the temperature of the environment is allowed to relax back down to room temperature over the remaining 7 hours or so. And using the lateral position data, we're able to calculate the change in how the mirror mounts pitch and yaw, or tip and tilt, change over time, plotting those angular deviations or deflection angles over the same time for each mount in red and blue, respectively. Mount 1 is an industry standard mirror mount, which shows how the deflection angles, the red and blue lines there, change more drastically than Mount 2 and do not return to their original position over time. This is a prime example of the thermal hysteresis problem that we discussed earlier and depicts the impact on optical alignment stability when those problem areas are not taken into account. Mount 2, on the other hand, depicts a solution to those thermal swings, showcasing the more limited change in deflection angle during that thermal shock, but more importantly, the return of the pitch and yaw measurements back to their original starting position as the temperature returns to normal. And you can see that pretty much at the tail end here, the pitch and yaw in red and blue are going to come back down to that zero line, which is important to maintain stability. So how did we improve that stability? How did Mount 2 in the last thermal shock scenario and the vibration testing move past those problem areas? Well, it took remember that the optomechanics, basically how the optics are mounted, are going to be the most important parts. So when it comes to thermal instability, heat-treated materials with low coefficients of thermal expansion were used. When it comes to crosstalk, tighter tolerances are used on the machine parts to ensure orthogonality, and harder materials are used to maintain that structural integrity over time to prevent that wear and tear. For backlash and drift, the matched thread pairs, where the adjuster screws meet the back plate or a bushing of a mount, they're matched to minimize lubricant, and we also minimize the number of different components, as more components can lead to more potential problem areas and more degrees of freedom. When it comes to external vibrations, stiffer springs are used along with some of the other solutions mentioned above. Ultimately, hours of extensive research, multiple design efforts with sophisticated design tools like finite element analysis software, months and years of rigorous testing around each of these key problems went into choosing the best components to really give that ideal solution for ultra-stable performance. So in finding that solution, some design considerations to take into account for alignment stability include material selection or treatment, match threads, hardened contact points where you get the most movement, the way you're holding your optic or optic retention, and cleaning and testing of each and every mount. As shown in the picture, the Polaris mirror mounts from Thorlabs are going to be the best-in-class solution for applications that require stringent long-term alignment stability. These key factors were considered when we designed our Polaris mounts. Let's take a deeper dive into those design considerations now. All right, so the first design consideration are going to be the materials. When building our Polaris mirror mounts, We tested dozens of different types of steel alone just to figure out which works best for different thermal swings, vibration swings, etc. We got the best raw material suppliers to keep quality and consistency. The materials themselves are made from stainless steel and are heat treated and stress relieved, as well as having low coefficients of thermal expansion. Compare that to an industry standard mount, which are typically aluminum or might even have a bushing material that's different than the back plate to hold the adjuster screw, perhaps brass or bronze or something along those lines. All different materials with different thermal expansion rates. The heat treatment itself removes internal stresses that cause the temperature-dependent hysteresis, and ultimately, all of these factors help minimize thermal instabilities. Another design consideration are matched threads. This basically means matching the external threads of your adjuster screws, 3 of which are shown on the back plate of the Polaris K1E3 in the lower image, and a thread and bushing pair in the upper right. By matching threads using a Swiss screw machine to specific production lots, you're able to minimize backlash and ultimately get a near interference fit, so greater than class 3 thread tolerances. This lets you use minimal lubrication to prevent that kind of drift over time, and long thread engagement, more contact between the internal and externally threaded mating matched pairs, also helps with that longer term stability. The next design consideration are going to be the sapphire contact pads, or points of contact from the adjuster screw to where it hits the front plate shown here of your kinematic mirror mount. The sapphire itself reduces friction since it's a much lower coefficient of static friction against steel, and it maintains the integrity of those contact points. We've actually tested mounts from 15 years ago that are still used in testing today. And the contact pads where the ball tips of your adjuster screws hit those sapphire plates, they haven't deteriorated in performance from wearing out those pads. So if it can last 15 years, these contact pads will last a lifetime. The dimensional tolerances on the front and back plates as well are tightly controlled. So the placement of those contact pads, as well as all the dimensions on machining each of the parts, are kept very precisely controlled, and ultimately this maximizes your orthogonality or perpendicularity between your axes of adjustment, which in other words means minimizing the crosstalk. So you'll get less and next to no unwanted movement from adjusting one axis through another axis. Optic retention, or how the optic is held, is another design consideration when trying to build your ultra-stable kinematic mirror mount. We already talked about the materials and contact points for key movement zones from the threads and adjuster tip seats, but what about the contact points on the optic? So for our Polaris mounts, the bores are precision machined to achieve the fit that will give the optimum beam pointing stability over changing environmental conditions from shock to temperature swings, etc. It's important for that pointing stability and low optical distortion, so you don't get as distorted of a wavefront when bouncing off a mirror, for instance. We have a few different types of optic retention mounts, but pictured here I'll show 2 of them. One is the patented monolithic flexure arm shown below. Monolithic just meaning made from a single piece, as opposed to kind of a flexing spring or some other arm. This arm shown right here along this ridge is all made from the same mount material. So the entire faceplate, including that arm, are considered monolithic. We tested these mounts to get the right angle and the right torque for mounting the optic so that you're able to stably hold your optic in place to keep that pointing stability while minimizing the amount of distortion from too much torque as well. On the right-hand side, we have our patented low distortion mirror mounts, which have the optic, a mirror you can mount in the front in green. Right behind it is a little wave spring in red, and behind that is a patented retaining ring with a calibrated adjustment stop in blue. And what that allows is putting a very even pressure on the mount to avoid any distortion on the front surface. The three scans here, right above the low distortion mount, were taken using a Zygo interferometer to test the wavefront errors or distortion on a mirror. The two left-hand images of those three are shown with the low distortion Polaris mirror mount. And you can see 3 dots on each of these. Just point right here. You can see the 3 dots where the 3 contact pads to hold the optic in place are. Those are going to be outside of your clear aperture anyway, but the rest is extremely smooth from a surface standpoint. Compare that to the traditional set screw holding of a mount, where a set screw clamps down on the side. You can even kind of consider my upper right arrow as a set screw. That adds a lot of pressure on the side of the mount, which distorts the front surface. And you can clearly see the differences in the surface of your mirror here. Moving on from there, the last design consideration to consider is the cleaning and testing of your mount. When we make our Polaris mounts, we ultrasonic clean all the parts. We bead blast the main components, as well as passivate the stainless steel front and back plate along with some of the adjuster screws. And we put them in a double vacuum bagging to ensure that no contaminants are in that packaging when it arrives at the customer site. You can see the packaging of a mount on the picture here. Ultimately, by removing those contaminants and making sure it's very clean, we give the smoothest possible surfaces, as any little scratches or lack of smoothness can actually impact alignment stability. You can think of those scratches or lack of smoothness creating high stress concentrations in the materials, which over time and through any thermal or vibrational shocks can impact stability. Dust particles or contaminants as well can interrupt the intended optic contact points for true kinematic motion and also throw off the alignment. Every single Polaris mount goes through the testing that we've talked about so far to make sure the performance is verified. So when buying a mirror mount for a very ultra-stable application, you do want to make sure that the mounts are thoroughly tested each and every time to make sure that the performance is good to go as soon as it arrives. Now, what does the outcome of all these design considerations look like? Here's an expanded view of that same thermal shock test shown earlier to exemplify how optical alignment can remain stable after a big temperature swing. So you might recognize on the left the temperature in blue this time, and the change in deflection angle over that temperature change in green and red. And you'll note on the right-hand side, after about 2 hours, as the temperature returns to normal, the deflection angles measured with our Polaris mounts returns to the original position within 1 microradian. So your optical alignment is secure. So the Polaris K1, which was our first mount released in 2009, started in development almost 20 years ago to fix those key optical alignment stability problem areas. Since then, we've engineered new solutions, often based on customer feedback and to meet the growing needs of different applications, while using the same design considerations and rigorous testing that have driven the Polaris product line as a whole. After that release in 2009 of the first Polaris mount, we added a mount for smaller half-inch optics as the need for space saving increased. From there, we engineered more ways over the next couple of years to hold your optic, to reduce stress on the optic itself, like the low distortion mount pictured. We developed different methods of adjustment, like our piezo actuators that enable smooth coarse and five movements along each axis. The Polaris piezo actuators pictured there in 2014 use a voltage to kind of give you a dual motion, both in coarse and five movements. We enhanced our side clamping retention method using the monolithic mount, discussed a little bit earlier. That was in 2015. And we added glue-in mounts for more permanent applications that don't want any user-supplied forces, along with platform mounts for stably holding and adjusting non-round optics with the same Polaris design considerations as before. Over the next years, we expanded the product line to account for more optic diameters and actuation methods. Just 4 years ago, we released the first vertical-drive Polaris mount to solve user issues of not having enough space or dexterity to turn the adjuster screws in space-constrained applications. We'll dive into the vertical drives a little later. But to kind of show different application requirements, just a couple years ago, we expanded even further with a bimetal ruggedized mount, the larger one shown on the top right. That is designed for extreme temperature changes and for larger optics, more often for laser, high-power laser applications. We also released 5-axis and XY translation mounts, all while maintaining that same alignment stability you'd come to expect from trying to design the most stable solution to keep that optical alignment. And just earlier this year, we released the 1/2-inch diameter optic vertical-drive Polaris mount. This again was driven by customer feedback and the application needs to save on space. We're really excited about this mount, this latest release, so let's dive into that a little bit further. So the vertical drive mounts use a piston adjustment mechanism that isolates the front plate from unwanted forces. They are patented vertical adjusters, and our stock ones use a monolithic flexure arm design. Ultimately, what this allows is the ease of access to the knob for space-constrained setups. Sometimes you really can't afford the space behind your mount horizontally to kind of turn the adjuster screws, so you really need to access it from the top. It's an overall compact footprint and the ability to swap front plates for different applications as well. If the flexure arm faceplate isn't really perfect, we can mix and match different Polaris styles to suit your needs. So through that last 15 years of working around different customer application needs, we now have a variety of Polaris products to suit different applications. So if you don't find something that works for your application, we're all ears for any feedback, of course. And here's just a quick overview summary of those offerings that all keep those design considerations for an ultra-stable mirror mount. We have different optic sizes that can be accommodated, from 1/2-inch diameter to 6-inch round optics, along with platform mounts for any prisms or beam splitter cubes, for instance. In the table on the top right, that shows a few different retention methods. We already talked about the side locking and the low distortion mounts a little bit, but we also have threaded, SM threaded mounts for other common optic housings, as well as glue-in mounts for the more permanent solution that can avoid any clear aperture issues, especially if you're looking to pick off a certain edge of a laser. And different adjuster types as well, from simple adjuster knobs to driving with a hex key or ball driver, along with the vertical drive adjusters that we talked about. And with that, that covers our talk here today with about 30 minutes. While we're out of time to dive too deeply into these, I should mention that you should also consider your fixed hardware to hold these mounts to your optical service and other parts in your system. To avoid similar optomechanical problem areas, we've taken those same design considerations for our Polaris mounts onto hardware like washers and optical posts and even table clamps. The table clamps especially, often industry standard table clamps can create sort of a bridging clamping arm. We've engineered Polaris clamping arms that are non-bridging to eliminate that deformation on your breadboard or table. So if you want to talk about these further, our tech support team and I were both happy to talk about these. So feel free to reach out if interested. And with that, thank you for your attendance. I hope you learned something, and or maybe even just to think about your optical alignment stability in further detail. thank you again.
Thank you, Lucas, for that informative presentation. We have a few questions to go through, so we'll see how many we get through before we run out of time today. So to start us off, the first question would be, was the thermal cycle you showed the first after mounting of the mirrors, or are there initial jumps, drifts that won't appear after a few cycles? So with the thermal cycling that you showed, kind of, at least how I'm interpreting that, would you see those same spikes if you did it repeatedly?
Yes, so we've done a variety of thermal testing. Depending on the temperature chosen, the ramp up rate, you'll see similar spikes as the temperature increases and decreases. The kind of key feature that we're looking to show ultimately is if you do return back down to your initial temperature, whether it's room temperature or some set standard, all the tests we've run on the Polaris mounts will come back to that original position.
All right. The next question, are the sapphire seats glued into the plates?
Yes,
I'm not sure if that's, yeah. Okay. And then let's see. Are the mounts lockable?
Yeah, that's a great question. Just to add on to the sapphire seats too, we
Sure.
we use a vacuum compatible epoxy when assembling these. So if that were a concern, it shouldn't be. They're glued in and with the same clean room and vacuum standards. As far as lockability, I'll show our slide here. I think this hopefully is the best picture to depict that, but we do have lock nuts for all of our adjusters. So while the front plate itself is not technically locked to the back plate, the springs are going to be very stiff and will hold that kind of locking in place, especially through the shaker plate testing like you saw before. But when it comes to shipping these elsewhere, where you don't want the screw itself to move and thus move the front plate, we do include lock nuts. And online we have different torques for kind of a short-term and long-term shipping or locking as well. So these are thoroughly tested for different shipping constraints and locking over time.
All right, and then I've got two that are in a similar vein. Are there plans for vertical drives with low distortion mounting of the optics? And are there plans for remotely controllable versions that would be able to stay in their position rather than losing if the power's cut, for instance? Because I know piezo's, if I'm not mistaken, can reset.
Right. So at least in regards to the low distortion, we do have those as a kind of a made to order, not on the catalog as far as I have seen, but we can certainly make those to order. So we can take the front plate from a low distortion catalog mount, swap it onto the back plate of a vertical drive, and certainly ship that out with a reasonable lead time just for that quick assembly. And in regards to locking if the power's cut, yeah, I think the piezo adjusters currently would kind of have that same feature where if you do cut off a voltage, the piezos will relax back to their kind of zeroed position. Longer term, I think that would certainly be a good place to look into. So yeah, it's a great feedback.
Let me see. I think we have time for one more question. Let me take a look at what we got. Are there any broad application areas that call for features like the ruggedized Polaris mounts that we have?
It's good. They were so they were designed with high power laser systems in mind, but even when it comes to heavier thermal cycling, and larger optics in general, the larger the optic, kind of the more weight involved and the more room for potential errors if you don't kind of build the mount appropriately. So I think even though high power lasers were the kind of the push behind them. Anything with larger optics or significant temperature swings or vibrations, I think would be a good general application space for them.
All right, excellent. I think that's pretty much all the time we have available for today. Thanks again, Lucas, for the presentation. Our next webinar will be hosted by Photonics Media on July 24th, where Thorlabs' Carol Borsa will discuss beam steering with galvos. You can register for the event on our website at www.thorlabs.com/webinars. Thank you very much for your attendance at this talk, and we hope to see you again.